Hello and welcome to another lecture of this course, Mathematics for Economics Part 1. Right now what we are doing is that we are doing some tutorials. These tutorials hopefully will help you to revise some of the topics that we have covered in this course and also to develop some skills of problem solving, because theory is fine. What we did mostly in this course is discussing the theory, but as we know, problem solving skill is also important. So, in this series of tutorials we are going to solve certain problems from the topics that we have covered. So, as you can see on your screen, so we are talking about the first set of tutorials, tutorial 1, and the topics that we have covered in this tutorial so far are we talked about real numbers and mathematical logic. We also talked about sets and set operations. The last topic that we started with in the last lecture was on differentiation, right? That is what we just started with. So, let us go to that problem that we discussed in the last lecture. So, this was the problem that we were discussing. Let me just revise this a little bit, and so that we can go forward. F p is the demand function of a product, where p is the price per unit of the good, and given this demand function, the total revenue function is denoted by T r, which is again a function of p, and T r p is equal to p multiplied by F p, that is price multiplied by the demand. Find an expression for T r prime p, that is the derivative of the T r with respect to the price, that is T r prime p, and that is what we did. We have started with T r p, we have used the definition total revenue is equal to price multiplied by demand. Demand is given by F p, so it is p multiplied by F p. Then we took the first derivative of total revenue with respect to price, and this is what we get, DTP of p multiplied by F p, and then we use the product rule of differentiation in the next step, okay, and then we get, so p multiplied by DTP of F p plus F p multiplied by dP dP, and that with some manipulation gives us this expression. If we take F p common, then within the brackets we have this expression 1 plus p divided by F p multiplied by F prime of p. Here remember, F p is the demand function. Demand function is a function of the price, and as we have noted here, F prime p multiplied by p divided by F p is called the price elasticity of demand. All right. This we shall deal with later on also in more detail, but let us try to see what it decomposes into. F prime p is what? It is d F p dP, this is F prime p, and that is getting multiplied by p divided by F p, right. This is what the elasticity of demand is, price elasticity of demand. Okay. And if we denote this by, let us suppose, simply as small e, then what we are getting is total revenue, the derivative of that with respect to price is equal to f p multiplied by 1 plus e, right, and f p is nothing but the demand. So, demand at that particular price multiplied by 1 plus price elasticity of demand. Okay. So, this is what the T r prime p is. So, this is the answer. I have just added these comments so that the listeners or the students who are undergoing this course are aware of the implications of the result. Result is fine. So, the result is just this much, right. Here is the result, but the result also has an implication. So, this is the implication of that, that if you take the derivative of total revenue with respect to price, then this is what we get. It is actually a function of the price elasticity of demand. Okay, this is a related problem. Suppose that for a monopolist firm, there is a level of output where its profit is maximized. It is known that its marginal cost and price elasticity of demand are 1 and -2 respectively. What is its equilibrium profit maximizing price, given that in equilibrium marginal revenue and marginal cost are equal? Okay. So, there are certain information that we are given here, that there is this monopolist firm. We have talked about what is a monopoly before. So, I am not going to spend time on that, and this monopolist firm is maximizing its profit, right. So, there is one output where its profit is maximized. It is also known that the marginal cost and the price elasticity of demand of this firm is given by 1 and -2. What is further given is that in this equilibrium where the profit is getting maximized, MR marginal revenue and MC, they are equal. So, MR is equal to MC. So, that is what determines the profit maximizing output. We have to find out what is the price at that equilibrium. So, what is the price that will be charged in the market because the firm is maximizing its profit. So, that is the question. Okay. How do we solve this? We start with the total revenue function. As we know, total revenue is equal to price multiplied by quantity, P multiplied by Q, and from here we try to get what is the expression for marginal revenue. As we know, if we take the derivative of the total revenue with respect to quantity, then we get the marginal revenue. So, DDQ of total revenue, right. Total revenue can be thought of as a function of quantity. So, this is what we are trying to get. This is MR. So, we have basically used the fact that T r is equal to P multiplied by Q, and then we have taken the derivative of P Q with respect to Q. So, once again product rule, but mind you, compared to the previous problem here, the variable with respect to which the differentiation is being done is not price, it is quantity. All right. So, this is what we will get. We take P common. So, if I take P common, it becomes 1 plus Q divided by P multiplied by dP dQ, and this can be written in terms of the elasticity, right. In the previous problem itself, we have seen that small e can be denoted as the price elasticity of demand, and small e is given by this expression, right. This is nothing but P divided by Q multiplied by dq dp, and here we are actually talking about the reciprocal of that E. Okay. So, that is why I have written this as 1 divided by E. So, the upshot of this small exercise is that marginal revenue is equal to price multiplied by 1 plus 1 divided by E. All right. Now, that is just one step. Now, as we know further, it is given in the question that at the point of profit maximization, MR is equal to MC, okay, that is given. Now, we use that fact and the fact that marginal revenue is this, the left hand side, P multiplied by 1 plus 1 divided by E, and that is equal to MC in the equilibrium. And then we express the thing in terms of P. On the left hand side, I only have the price, and on the right hand side, if I take those terms there, I get MC multiplied by E divided by 1 plus E. So, this is an important expression. Price in a monopoly market is equal to marginal cost multiplied by E divided by 1 plus E. So, as long as the elasticity is suppose constant, then price has to be fraction, in particular E divided by 1 plus E will be greater than 1. So, price will be some quantity, constant quantity multiplied by the marginal cost. It is something, sort of markup over the marginal cost. This is called markup. Okay. But here our problem is somewhat different. We have to find out the price. We are given the fact that the marginal cost is 1, elasticity is -2. So, we put these values here, right, MC is equal to 1, E is equal to -2. If we put them in this expression, then this is what we get, P is equal to 1 multiplied by -2 divided by -1, and that is simply 2. So, this is the equilibrium profit maximizing price, right, price is equal to 2. So, this is our solution. Now, again as a commentary, notice that in the equilibrium the marginal cost is 1 and the price is more than that marginal cost, right, it is 2. So, the marginal cost is added with something, with some markup, and then we are getting the price. Okay, so, this is the answer. Here is another problem, and this is related to the economy of poor countries, the agricultural economy of poor countries. So, it could be very relevant for countries like India, where the agricultural sector is a large sector, it employs a lot of people. Actually, it is the largest employer in the Indian economy. So, what goes on in the agricultural sector, that is an important question, and this problem is trying to answer some of the things that are important in the agricultural sector of a poor country. Suppose agriculture firms production function is given by this, Q is equal to capital A multiplied by log natural of L plus 1, where L is labor employment, capital L is labor employment, and capital A, which is multiplied with this log function, is greater than 0. Price of agricultural good is given to be 1, wage rate of labor is W, small w. So, this is the setting. Then we are having two questions here. The first one is the owner of firm X decides on labor employment by the rule, this rule, price multiplied the marginal product of labor is equal to wage rate. Okay, so, this rule decides how much labor the owner of firm X will employ. So, we have to find out how much labor, let us call that L star, will be employed, and furthermore we have to find out del L star del W and del L star del A. So, these are partial derivatives of L star with respect to W and A. Those things we have to estimate. This is the first part. Second part, suppose the owner of firm Y has a family with labor endowment L0, okay, which is employed on the family farm because job is scarce in the village. L0 is greater than L star. Call the additional labor employment in Y compared to X as U, and U is a function of small w, as we shall see. What we need to answer is that what is the nature of UW function. Okay. So, this is the second part. We have to find out the nature of this U function. Just to think about it, how to approach the problem and what this problem is trying to say. So, there are two firms in this agrarian economy, X and Y. X is a firm where the owner is deciding the employment, labor employment on the firm by this rule, price multiplied by marginal product of labor is equal to wage rate, right. And from this rule, the L, that is labor employment, can be found out, that we shall see, and that employment is given by L star. So, this is one kind of firm. The other kind of firm which is there in the part 2 is the Y firm, where the employment decision is not decided by this price multiplied by marginal product of labor is equal to wage rate, but it is decided by how much labor is there in the family which owns that firm. Okay. So, the family is endowed with L0 amount of labor, and that labor will be employed on the firm, right, irrespective of what the wage rate is. So, this rule is not applicable. Okay. And what we are assuming is L0 is greater than L star, right. There will be condition under which L0 will be greater than L star, we shall see that, and then we are trying to find out what is the additional employment that will be done in firm Y as compared to firm X, right. So, the first firm is like a capitalist firm. It is also called a capitalist firm, where the owner does not have family labor to take care of. He is like a profit maximizing capitalist producer. He tries to maximize profit, and that profit maximization, as we shall see later on, gives us this rule, price multiplied by marginal product of labor is equal to wage rate. Now, that is one principle of how much labor to employ. On the other hand, a firm might be owned by a family, and the family has plenty of labor to employ, and since there is unemployment in the economy, that family endowment of labor will be put on the firm, because jobs are difficult to come by. So, the people who are there in the family work on their own firm, okay. And so, L0 will be employed, L0 amount of labor will be employed. So, we are trying to see the relationship between L0 and L star. So, that is the background of this problem. It is a very important and quite familiar problem in the literature of development economics. Okay, let me start with the first part. This is the firm X, and employment in firm X is decided by this rule, as we have seen in the problem. Price multiplied by the marginal product of labor is equal to the wage rate. Now, out of these three things, price and wage rate are known to us. Marginal product of labor is not known to us, but that can be found out from the production function. Production function is given by this: Q is equal to A multiplied by log natural of L plus 1. Here just few words about the nature of the function. Here L is the employment of labor. Notice what we are getting here is ln, that is log natural of L plus 1, right. It is not simply L. The reason is, as we know, labor employment cannot be negative, it can take the value of 0 or positive amount of labor. Now, the trouble with log function is that at L is equal to 0, right. Suppose you are taking this kind of x and here you are taking log x and here is suppose 1, then here it is 0, but if it is less than 1, x is less than 1, then it becomes negative out. Now, if I had taken log of L, then it would have been very difficult to interpret this function, because that would have meant that if labor is less than 1 greater than 0, then output is negative, which is difficult to justify, or it is difficult to justify why if you have labor employment 0, the output is minus infinity. Okay. So, those things can be avoided if we take this form log of L plus 1. So, here even if you take L, the minimum value is 0, it gives you log of 1, log of 1 is 0. So, that is fine. And then there is this constant term which is capital A. What is the significance of this capital A? Capital A is kind of productivity parameter, okay, can be thought of as the amount by which this ln L plus 1 is getting multiplied to give us the output. So, you can think about a high A and a small a. If you have a high A, large A, then the same L will give you a lot of output, but if you have small a, that same L will give you less output, right. So, this A is actually shifting the production function, right. It will be like this, as you have high A, it is shifting upwards. Okay. So, that is why I am saying that it is kind of the technology, right, kind of the indication of how developed the technology is for agricultural production. Now, the main point is that we have to find out the marginal product of labor from this function, from this production function. Now, as we know, the marginal product of labor is found out by taking the derivative. Here it will be partial derivative, because a might also vary. So, I take the partial derivative of q with respect to L, and that gives me a divided by L plus 1, okay, a simple derivative of a logarithmic function. And then we apply this rule, price multiplied by marginal product of labor is equal to the wage rate. So, there I put price is equal to 1, wage rate is equal to W, and marginal product of labor is equal to A divided by L plus 1, and we get simply this, all right, very simple looking function. Then we actually try to find out what is L. So, in the next step we get this, L is equal to A divided by W minus 1, and this, as we have seen in the question, is termed as L star. There you can see how much labor L star will be employed, that we have just found out. it is given by A divided by W minus 1. Now, the next step is to find out the partial derivatives. So, for that I have taken the partial derivative of L star with respect to W, and if we take the derivative with respect to capital A, it is simply 1 divided by W. What is the implication? Once again, let us try to understand what is the implication. L star is the equilibrium employment or the optimal employment to be done by the owner of firm X. The owner of firm X is a profit maximizing farmer, and he is employing L star, but that L star can vary with respect to two things. One is the wage rate. As wage rate rises, we are getting L star to be declining, because it is a negative thing, right. Del L star del W is negative. In simple terms, as the wage rate in the market rises, the owner of firm X is going to reduce the employment. On the other hand, as A, that is capital A, rises, L star will rise, because del L star del A is 1 divided by W, which is positive. So, as the technology becomes more productive, the owner of firm X will employ more labor on his firm. So, that is what the meaning of these two terms is. The second part, we are talking now about the other firm, which is Y. Firm Y employment is determined by the family labor endowment. So, again to recall, Y is not owned by a profit maximizing farmer. It is owned by someone who has a family to look after, and that family has L0 amount of labor endowment, right. So, that L0 is employed on that firm, as we are told in the question. Therefore, the additional labor employment in Y compared to X is given by this UW, which is given in the question. UW is L0 minus L star, right. How much is the difference between the employment in the family firm, that is L0, and the employment in the other firm, capitalist firm. So, that is L star, right. So, this is what we are getting. UW is equal to a function of W, and I write the expression for L star, which is this A divided by W minus 1, and thereafter I take the partial derivative of UW with respect to W, and I get simply A divided by W square, and which is positive. Okay. So, this is the answer. We were asked to find out the nature of the UW function, and I have taken the partial derivative of UW with respect to W and found it to be positive. So, UW is an increasing function of the wage rate, which basically means that as the wage rate in the market rises, the additional employment in the family firm compared to the X firm, that is the capitalist firm, that additional employment is actually rising. Now, UW has a name, actually it is sometimes called the disguised unemployment. This additional labor employment in the family firm is compared to the X firm is sometimes known as disguised unemployment. Those of you who will be doing courses on development economics will be quite familiar with these expressions. Okay, here we take up another problem related to differentiation. Let a function of t, be the distance traveled by a car in t hours measured in kilometers. Let P A be the amount of petrol the car consumes to cover a kilometers. What is the interpretation of the function L t, which is P of A of t? Estimate L prime t and interpret it. Okay, so, this is the question. Let us try to understand the question. Two functions are given. A is the distance, right, it is in terms of kilometers, and it is a function of t, right. How much time is spent in traveling, and that affects the amount of distance covered, right, and that distance is given by A. On the other hand, if you are covering more distance, the petrol consumed also rises. So, P is the petrol consumed, obviously P will be a function of A. Now, both of these will be increasing functions, both A and P. We have to find the interpretation of the function L. So, L function is defined as P of A of t. Okay, so, interpretation is the following, that L t is equal to P of A of t is the liters of petrol the car consumes for traveling t hours. Here petrol is a function, or liters of petrol is a function of the time, right. It is not like P A. In P A, liters of petrol was a function of distance, here it is a function of time. Here the independent variable is not distance, but time t, which in turn affects A, thus affecting fuel consumption. So, this is easy to understand. So, t is there, time, it affects distance A, and distance affects petrol, that is how much petrol is being consumed. So, ultimately P is a function of t, right, and that is being written here as L of t. Secondly, what is L prime t? L prime t, the derivative of the L function with respect to time. So, that is d dt of L t, and that we write it as following, because I know L t is equal to P of A of t. So, I write that explicitly, right, and then I take the derivative of this using the chain rule of differentiation, and that will give us dP dA multiplied by dA dt, where A is a function of time. Now, I also know P is also a function of A. So, this becomes P prime A, and the second term is nothing but A prime t. So, in short, L prime t is equal to P prime A multiplied by A prime t. So, this is what we are getting. L prime t, that is the derivative of the liters of petrol consumption with respect to time, is equal to P prime A multiplied by A prime t. The rate of change of petrol consumed with respect to time is equal to the product of rate of change of petrol consumption with respect to distance and rate of change of distance travelled with respect to time. Okay. So, that is the interpretation in terms of words. Okay, here is a sort of different problem. Here the problem is macroeconomic, a macroeconomy which is closed and without a government is modeled by the following two equations: y is equal to c plus I and c is equal to f of y. The marginal propensity to consume, that is f prime y, lies between 0 and 1. So, I can write it simply as this, okay, f prime y, it lies between 0 and 1. Now, there are three parts to this problem. given this setting. Suppose C of f of y is this. So, it is taking this particular form 20 plus 0.9 into y. Use equations 1 and 2 above to find y in terms of I. If I changes by del I, how much or what is del y? Del y is change of y. This is the first part. Second part, find the expression for dy di if f y is given by this 20 plus 0.9 y, and in general means f y is having this form, f y is just f y, it is not taking any particular form. And finally, find the expression for d square y d I square in general. In general means again, suppose f y is just f y. So, these are the three parts of the problem. Let us start with this two equations that we are given. This is one equation, number 1, y is equal to c plus I, and number 2 is c is equal to f of y. If we combine them, so I substitute c is equal to f y here in the first equation, I am getting y is equal to f of y plus I. And I have been given the form of f of y, it is this 20 plus 0.9 y, I am using that. And now I can express y as a function of I. So, that is what I am doing, I am taking all the y terms to the left hand side, and after that I get this y multiplied by 1 minus 0.9 is equal to 20 plus I. So, I can divide both sides by 1 minus 0.9, 1 minus 0.9 is 0.1. So, I am dividing both sides by 0.1. So, that is what I am getting 20 plus I divided by 0.1, that turns out to be 200 plus 10 I. So, y is equal to 200 plus 10 I. That I think was one question that was asked, to find y in terms of I. That is what we have done. Here y is the dependent variable and I is the independent variable. I have expressed y in terms of I. The second part here in the first question itself was, if I changes by del I, then how much does y change? So, to do that, let us try to see if I changes by del I, the new I is I plus del I. So, that I substitute here, right. In that case, y will change to a new y. So, suppose that new y is given by y plus del y, right. So, y plus del y will be 200 plus 10 multiplied by new I. And what is the new I? New I is I plus del I. And we take this equation and we take this equation, we subtract this one from this one, then if we do so, then we shall get del y is equal to 10 multiplied by del I. I think that was the second part. Second part was, if I changes by del I, what is del y, right? Then del y is equal to 10 multiplied by del I. Okay, now we come to B. B is what? Find the expression for del y del I for this particular form of f y and in general. Okay, we again start with the equation that we have just derived, this one, right. We start with that and we take the differential of both sides and we are going to get del y is equal to 10 multiplied by del I. The reason is 200 is a constant, so it will drop out. Y and I are the variables, so we take the differentials and so we get dy is equal to 10 multiplied by di, and in the next step I simply get dy is equal to 10. This actually can be expressed as the following: dy is equal to 10, and that can be written as 1 divided by 0.1 turns out to be 1 divided by 1 minus the marginal propensity to consume. 0.9 was the marginal propensity to consume, remember, right. If you have this consumption function, then 0.9 is equal to MPC, or marginal propensity to consume. Okay. So, that is what we have written here, that 1 minus 0.9 is equal to 1 minus the marginal propensity to consume. So, dy di is 1 divided by 1 minus marginal propensity to consume. This is also known as the investment multiplier in the simple Keynesian model. So, this sort of model is called a simple Keynesian model, and in this kind of model dy di is called the marginal propensity to consume, and in this model it is given by 1 divided by 1 minus the MPC, marginal propensity to consume. But this was the case where the consumption function was having this particular form, right. The form was this form 20 plus 0.9 y. But suppose I take a general consumption function of Fy instead of this linear form, then what do we get? This is what I get by taking the differential of both sides. Dy is equal to f prime y dy plus di. Again I take all the dy terms to one side. So, dy multiplied by 1 minus d prime y is equal to di, and in the next step I am going to get dy di is equal to 1 divided by 1 minus f prime y. Again, if you remember, f prime y is MPC, right. So, previously when the form was given, linear form, the MPC was 0.9. So, that is what was appearing here. But if I take Fy to be the general consumption function, then f prime y is the MPC. That is why here instead of 0.9 I am getting f prime y. Okay. So, the basic form of the investment multiplier remains the same. It is 1 divided by 1 minus MPC. All right. Now, the third part, C. Third part is we have to find out this, the second derivative, d square y di square. Dy di was found out, right. It is called the investment multiplier, but if I take the second derivative of y with respect to I, then what do we get? Okay, the first derivative is this, right. We are talking about the general form. I am not taking that linear consumption function. Now, differentiating both sides with respect to I, that is what we get to get the second derivative. So, that is what we are doing here. Now, here to simplify this, I am using the chain rule. I am assuming that u is equal to 1 minus f prime y. So, if I do so, then this expression becomes 1 divided by u, right, and if I have I here, I cannot differentiate the function if it is a function of u. So, I write du here, and using the chain rule I write du dy and dy di. Okay. In the next step, d du of 1 divided by u. So, what is that? It is minus of 1 divided by u square, right. So, minus of 1 divided u square is coming here because this was u, So, 1 divided by u square means 1 divided by 1 minus f prime of y whole square. Du dy, so I have to take the derivative of this with respect to y, and that will be minus of f double prime y, that is coming here, multiplied by dy di, and this is repeated here, and then I simplify it a little bit. I use the fact that dy di, that is nothing but the investment multiplier, is equal to 1 divided by 1 minus f prime y. So, this is what it is turning out to be. Remember, here is a minus sign and here is a minus sign, they are getting multiplied. So, they are cancelling each other. So, finally, I am going to get f double prime y divided by 1 minus f prime y whole cube. All right. So, this is the expression that we were supposed to find out. D square y di square is found out to be f double dashed y divided by 1 minus f dashed y whole cube. Okay, here is another problem from differentiation. What is the sign of the derivative of the function, this function a x divided by a x plus b of 1 minus x with respect to x, given that a and b are such that a multiplied b by b is greater than 0. So, this is the first part, we have to find out the derivative of this function. Second part, for a is equal to 1 and b is equal to 2, calculate f of 1 and f of 3. And thirdly, how are these two results consistent? So, two results means this result and this result, are they consistent? So, let us suppose that this function is given by f x, a function of x, we have to find out f prime x. That we find out by using the quotient rule, right. What was the quotient rule? 1 divided by the square of the denominator, right, x plus b multiplied by 1 minus x whole square, multiplied by the denominator a x plus b multiplied by 1 minus x, that is the denominator, multiplied by the derivative of the numerator, that is d dx of a x, minus the numerator a x multiplied by the derivative of the denominator, that is d dx of a x plus b multiplied by 1 minus x. So, this messy expression has to be simplified, and this is just simplification. Actually, many terms will get cancelled out at this stage, right, and if some terms are getting cancelled out, but only one term is remaining, which is a b in the numerator. So, f prime of x is equal to a b divided by a x plus b of 1 minus x whole square. Now, it is given that a b is greater than 0. Now, a b is greater than 0, that means numerator is positive. The denominator is positive always, right, as long as the denominator is not 0, it can be defined also. So, I have written that the denominator cannot afford to be 0 for f prime x to be meaningful. So, as long as the denominator is not 0, that is a x plus b multiplied by 1 minus x is not 0, the first derivative f prime x is positive. Okay. So, that is the answer to the first question, I think. First question was, what is the sign of the derivative of the function as long as a b is greater than 0? As long as a b is greater than 0, the sign is positive, provided the denominator is not 0. The second part is, what is the value of the function, that is f x, at x is equal to 1 and x is equal to 3, if a is equal to 1 and b is equal to 2. Okay. If a is equal to 1 and b is equal to 2, what is the value of f of 1? that is very simple. I have to use this expression, right. I have to put a is equal to 1 here, b is equal to 2 here, and x is equal to 1 here, and that turns out to be simply 1. Okay, f of 1 is equal to 1. Second is, what is f of 3? Okay. Again I use the functional form. This I put x is equal to 3 along with a is equal to 1, b is equal to 2, and I do the simplification. I get actually minus 3. Now, here is the sort of puzzle that we found out that f prime of x is greater than 0. F prime of x greater than 0 means what? That the function is something like this. I mean, this is just an illustration, it could have some other shape also, but it is a rising function if f prime x is greater than 0. Now, this seems to contradict the result that f of 1 is greater than f of 3, right. So, here is 1 and here is 3, f of 3 should have been greater than f of 1 if the function is increasing, but here it is less than f of 1, f of 3 is minus 3, whereas f of 1 is 1. So, how do we explain that? Well, the reason for this seeming puzzle is that f prime of x is greater than 0 is valid if the denominator is not 0, right. Denominator is not 0 means a x plus b multiplied by 1 minus x cannot be equal to 0. If that is equal to 0, then we are in trouble. Now, let us suppose if there is a problem somewhere. If a is equal to 1 and b is equal to 2, then this expression turns out to be this x plus 2 minus 2 x, and if you put x is equal to 2 here, right, where is 2? 2 is between 1 and 3. So, here is 2. Then actually this expression turns out to be 0, which means that the function that we are given f x, which is a x divided by a x plus b 1 minus x, this function is not continuous at x is equal to 2, it is not even defined at x is equal to 2. Okay. Now, that is basically creating the problem. What we have is something like this. Again, this is just an illustration, not an exact representation of this function. This function is discontinuous at x is equal to 2, at x is equal to 2 it is not defined. So, before x is equal to 2 it is, you can see it is increasing, after x is equal to 2 again it is increasing, right. So, in general the function is a rising function, right. That is what we found in the first part, f prime x is positive. However, at a particular point x is equal to 2, the function is not even defined. So, there is a discontinuity there, and that is basically the reconciliation of these two results. The function is in general a rising function except for the fact that it is not defined at x is equal to 2, and that is the reason why the value of the function before x is equal to 2 could be higher than the value of the function after x is equal to 2. So, there is no contradiction between the results that we obtained here. So, this is the reason, there is no contradiction, it is just that the function is not defined at a particular point. Okay. Here I am getting a little bit away from the differentiation theme. I am talking about sequences now. For the following sequences, comment if they converge or not. So, two sequences are given. As we know, sequences are generally denoted by Sn, right. Sn in the first part is given by 10 minus 3 divided by n square, In the second part, Sn is given by n plus 1 divided by n square. Okay, let us take the first one. Sn is equal to 10 minus 3 divided by n square. Now, we have to actually find out as n goes to infinity what happens to Sn. Now, here as n goes to infinity, the first term is 10, it does not change, right, it is constant. So, we can ignore it. What about the second term? Second term is minus 3 divided by n square. Now, as n goes to infinity, the denominator goes to infinity. As the denominator goes to infinity, the numerator is constant. So, the term actually goes to 0 as n goes to infinity. So, this part remains constant at 10 and this part, second part goes to 0. What happens to the entire thing? What happens to Sn? So, that is what I have written here. Limit n goes to infinity Sn is equal to limit n goes to infinity 10 minus 3 divided by n square, and that we have seen is equal to 10 because this part actually is going to 0, right. And as we know, that is the definition that if Sn goes to some constant, it tends to some constant as n goes to infinity, then the sequence converges. In this case, the sequence converges to 10. So, this is the answer, it is a sequence which converges. The second sequence is Sn is equal to n plus 1 divided by n square, and actually this can be simplified as 1 divided by n, 1 n will get cancelled from the numerator and the denominator in the first term, plus 1 divided by n square. Now, once again, as n goes to infinity, what happens to these two terms? As n goes to infinity, this first part again the denominator is going to infinity, which means that the fraction will go to 0. Similarly, here also the denominator goes to infinity, therefore, the fraction again goes to 0. So, both of them tend to 0. Therefore, limit n goes to infinity Sn is equal to limit n goes to infinity n plus 1 divided by n square, and that is equal to 0. Now, 0 is a constant, therefore, the sequence actually converges to 0. It is a case of convergence. I think that was the question. Comment if they converge or not. Yes, the second one also converges. All right, here is another problem in the same slide. The total coal reserve of a country is 100 billion tons. Its consumption is 2 billion tons this year, which is rising at 10% a year. How long will the coal last? So, it is a question of how fast a country will run out of its natural resources, a natural resource in this case which is non-renewable. So, there is a depletion, but there is no replenishment of that resource. So, if this resource is consumed and the consumption is rising over the time, then how fast will the resource be exhausted? So, that is the question. Now, how to get around this problem? The present coal consumption is 2, let us suppose I am just writing in terms of number, I am forgetting about the units, 2 billion tons, and it is rising at 10% per year. So, the coal consumption over the years can be represented by a geometric series given by the following: 2 in this year, in the next year it will be 2 plus 0.1 multiplied by 2, because it is rising at 10%, right, 10% a year. So, next year it will be 2 multiplied by 0.1, because 0.1 is equal to 10%. So, that is written as 2 common 1 plus 0.1. This is the second year. In the third year it will be 2 multiplied by 1 plus 0.1 whole square, and like this it will go on. In the fourth year it will be 2 multiplied by 1 plus 0.1 whole cube. Now, let us suppose that the reserve drops to 0 after t years. T is some constant. Suppose t is the number of years after which the reserve actually becomes 0, and we are assuming that there is no new discovery of coal reserve. Okay. In that case, what will happen after t years? How much is the total consumption? Total consumption is given by this, right. So, this is the last term in the tth year. Tth year's consumption will be this much, and this is the total consumption over the years, and that is getting equal to 100. 100 is the present reserve, right. So, since we are assuming that after t years the total reserve will be exhausted, so this relationship must hold. Now, the left hand side is a finite geometric series whose summation is given by this 2 multiplied by 1 plus 0.1 whole to the power t minus 1 divided by 1 plus 0.1 minus 1. This is the formula that we have discussed in the duration of the course, the summation of a finite geometric series. So, this is the formula, and so this simplifies to this expression, and we have to actually solve for capital T in this equation. The left hand side is the total consumption, the right hand side is the total reserve. And if we do so, actually this turns out to be very simple. Capital T is equal to log natural of 6 divided by log natural of 1.1, and if you have a calculator, it is easy to find out. It is approximately equal to 18.86. In other words, the coal reserve of the country will exhaust in nearly 19 years. It is very close to 19, 18.86. If consumption of coal continues to grow at the current rate, and that is important, we are assuming that all through these years, all through this t number of years, the consumption is rising by 10%, right. That is an assumption, so that we can apply this formula. If the consumption actually rises by a faster rate, let us suppose after some years, then actually the exhaustion of coal reserve will take place even with fewer years. And on the other hand, if people are more conscious of the environment, then maybe the consumption growth will slow down, and in that case the reserve will last for a longer duration. Okay. So, this is the answer to the question. Okay, this is the last I think the sum that we will do today, and then we will call it a day. A loan of 1 lakh rupees is to be repaid in equal annual amount of installments over 10 years. The first repayment starting 1 year from now. The interest rate is 6% per year. What is the amount of annual installment? All right. So, it is as if that you have taken a loan of 1 lakh rupees. Suppose you want to buy a car or maybe a house, you have taken some money from the bank. Now, that money you will repay over the next 10 years. And obviously, the bank will not give you a loan unless you pay some rate of interest. That rate of interest is 6% per year, right. Now, the question for you to solve, or maybe for the bank to solve, is that what is the amount of repayment that you will do per year. This is in Indian banking parlance, it is called the EMI, equal monthly installment, if you are paying it on a monthly basis. But suppose we are taking the payment per year instead of month, then the problem is similar. Then what is the amount that you will pay annually over the next 10 years, assuming that the payment per year is same. Okay. How to solve this problem? Here the amount of loan, suppose that is given by capital A. Capital A is 1 lakh. Time of repayment, what is the period over which the payment has to be done, that is given by capital T. Capital T is 10. The rate of interest is here given by 0.06, that is 6%, and that is suppose given by small r. Now, to obtain the amount of annual installment, and that is, let us suppose that is given by small a, we apply this formula. We have discussed this formula again during the course. Capital A is equal to small a divided by r multiplied by 1 minus 1 divided by 1 plus r whole to the power capital T. So, this formula actually is coming from the summation of geometric series, finite geometric series. You just have to review, go back to the books and the notes to remember that this was the formula. Now, I have to just substitute these values of capital A, that we know, R we know, capital T we know. What we do not know is small a, right, that is the annual installment, that we have to solve. So, I have substituted all these values in this formula, and in the next stage it becomes a little bit simpler. Again, I am taking the approximate values, 3 decimal places, all right, and so this turns out to be this, and in the next stage I get small a is equal to 13,574.66 rupees as the annual installment. Okay, so that is the answer. Now, just to get a hang of this, 13,000 is more than 10,000. Remember, if he had paid 10,000 per year for 10 years, then the total amount would have been 1 lakh rupees. 1 lakh rupees is the amount of loan. Here each year he is paying more than 10,000, he is paying about 3,500 rupees more than 10,000 rupees each year, and that is because he is paying the rate of interest, right, there is a 6% rate of interest. So, this additional 3,574 is due to the rate of interest component. If the rate of interest had been higher, suppose instead of 6% the rate of interest is 10%, then this 3,574 would have gone up, right. Each year he would be required to pay more if the rate of interest had been higher. Okay. So, this is one practical application which we often encounter in finance and economics of geometric series. Again, we are going to stop here because of lack of time, but we shall carry on with this series of tutorials in the next lecture as well. So, I hope to see you there. Thank you.